Okay, so now we're on to logarithmic functions. The logarithmic parent function is f of x equals log base b of x, which is very different from anything that you've seen before. What we're going to look at today is really just the shape of the graph and the relationship that it has with the exponential function, which is why we're studying them together. So if a b is greater than 1, which sounds pretty familiar, so let's pick a b value that's greater than 1, like maybe 2, then my function would say f of x is equal to log base 2 of x. Well, that was not nice. So log base 2 of x. And so over here, I'm going to graph log base 2 of x. Now this one's going to have an x-intercept at 1, 0. And it's going to have a vertical asymptote at x equals 0. So I'm going to go ahead and put that in on my graph here. Vertical asymptote, x equals 0, that's the y-axis. And then as I move to the left on this graph, or toward the asymptote, the curve is going to get closer to the asymptote, so it's going toward negative infinity there. And as I move to the right, it's going to move away. Kind of similar to what we were seeing with the exponential functions here. Now the reason for this is because the inverse of the logarithm function of this particular logarithm function is actually the exponential function with the same base. So this would be the inverse of y equals 2 to the power x. Now, if you recall, there's a relationship between functions and their inverses. I wanted to get a really light color here. Maybe I can do it in a highlighter. We'll try it with a highlighter. Okay, so the function y equals 2 to the power x would look like this. That's not right. Here, there we go. It would look like this, which is a reflection across the line y equals x. So let me see if I can get that put in there for you. There we go. So if I sketch that in there, you can see the relationship between those two. If I were to fold the paper across that line there, those two curves would lie right on top of each other. The one that's drawn in pink, of course, is my new logarithm parent function. So that's the shape of the graph if the b value is greater than 1. Now, if the b value is between 0 and 1, so I'll pick one of those, like a half. Let's keep it easy. Oops. I got to change my tool. Okay, so that would make it f of x equals log base 1/2 of x. This one still has an x-intercept at 1, 0, and it's still got a vertical asymptote at x equals 0, but the behavior of the curve is going to be different. So I'm going to go ahead and put in 1, 0 and the vertical asymptote there. This time, if the b is between 0 and 1, as you as you move toward the asymptote, it's going to go upward. And as you move away from the asymptote, it's going to go away. Sorry, as you move up, it goes toward the asymptote. As you move down, it goes away. Okay, so once again, this one is an inverse of another function. The inverse of this one would be the exponential function y equals 1/2 to the power x. So one more time, I want to put that the graph of y equals 1/2 to the power x on with this one. So that would look something like this. And then if I put in my line of symmetry, the y equals x, my graph is not perfect, of course, but if you were to fold the paper across that line there, then this piece of the graph up here would match up with this piece down here. And this piece up here would match up with this piece over here. So you can see that they would line up. They have that same symmetry that we talked about in the last unit. Okay, for all of these logarithm functions, the domain is going to be x is greater than 0 as long as there are no transformations, and the range is any real number. Now, much like with all of our inverses, these have the same relationship to the exponential functions. They just kind of reversed. So with exponential functions, the domain was all reals. With logarithms, it's the range. And this one has a vertical asymptote at x equals 0, which again kind of goes along with the inverses also. To find an inverse, you replace x with y and y with x. So on the exponentials, we had a horizontal asymptote at y equals 0. On the logarithm, you've got a vertical asymptote at x equals 0. All right, let's look at transformations. We have all the same transformations that we've had for every single function. We've got A, which is your vertical stretch or compression. It would be a stretch if the A is bigger than 1, and it would be a compression if the A is between 0 and 1. And then, of course, if you have a negative in front of the A, then that would reflect over the x-axis. Okay, if you replace the x with x minus h, well, the h would give you a horizontal translation. Once again, those are kind of opposite from what you think they ought to be. So if it said x minus 5 in there, then that means it would be going to the right 5. And if it said x plus 3, that would be going to the left 3. Okay, and then a final transformation there is the k on the end. That's your vertical translation. And those are exactly as they appear. So if it says plus, it's up. And if it says minus, it's down. Alrighty, so now we're ready to see a couple of examples here. So for our first one, we're going to be finding the base of the parent function, describe the transformations that occur to create the new function, then we'll state the equation of the asymptote, sketch the graph, and identify the domain and range. Okay, so our first one is f of x equals log base 2 of x minus 1 plus 3. The base of this one is 2, which means our parent function is going to be y equals log base 2 of x. Okay, so for transformations now, let's go ahead and state the asymptote on this one. It's x equals 0 for any of the parent functions there. And then, of course, we'll be using that point 1, 0 from this function in order to draw our new one. Okay, transformations now. The a value is just a 1, so that's no vertical stretch or compression, and it's not a translation either. Not a reflection either. We've got an h value of 1. It says x minus 1 within the function, so that means it's going to the right 1 unit. That looks terrible. Try that again. There. Okay, and the k value is a 3, so that means it's going to translate up 3. Okay, the vertical asymptote is going to be affected by any horizontal translations, because if you take a vertical line and you shift it up or down, it doesn't change. But if you shift it right or left, it does. So if I take x equals 0 and I shift it to the right 1, well, that would move it to x equals 1. So my vertical asymptote on this one, wow. Having major pen problems today. Let me try that again. Okay, so x equals 1. Okay, so now I'm ready to sketch the graph. Move the screen up just a little bit there. I'm going to start with a coordinate plane. I'm going to put in that asymptote. Put in that vertical asymptote. It's at x equals 1. And then I'm going to use the x-intercept from the parent function. And I'm going to translate that however it tells me to with the transformations. So this one says that I'm supposed to move to the right 1. So that means I would add 1 to the x value. So I would put it at 2, 0. And then I have to move it up 3. So that means I add 3 to the y value from that new point there. So that would be 2, 3. So the point that used to be at 1, 0 is now at 2, 3. So 2, 3 would be about right there. Okay, and now because the b value is a positive 2, that means from the point that I just plotted there, as I get closer to my x, to my vertical asymptote, it has to go downward. And as I move to the right, it would have to go away from the vertical asymptote. All right, so now looking at the domain, I can tell from my graph that it's everything to the right of that vertical asymptote. So that would be everything greater than 1. And for the range, well, the range on these are unaffected by any of our transformations. It's all real numbers. Alrighty, now you try one of the examples.